Welcome back. We now begin our study of forced convection, which is the next topic. Perhaps as you already know, forced convection is the presence of fluid flow along with heat transfer. And this fluid flow is caused by some external agency like a pump or blower. Typical situations for forced convection would be flow through a duct or a set of ducts when there is a blower or a pump. A cold fluid may be entering the duct. The duct is heated either because it is exposed to a hot fluid on the other side, maybe to a flame, or maybe an electric heater is wound on it. It picks up heat and goes out as warm or hot fluid. This is a typical, very common forced convection situation. Another situation is one in which you have a number of tubes, as in a heat exchanger. I am showing a cross section, and fluid is forced to flow over them. Tubes contain hot fluid, so their surface is at a higher temperature than that of the fluid. The fluid passes over and through the tube banks, becoming warmer. This is another forced convection situation. A third forced convection situation, not much different from this, is a gas turbine blade. Hot fluid from the combustion chamber flows around the blade. The blade may be stationary. If it's a stator blade, the blade may be rotating. If it is a rotor blade, and these hot gases expose this blade material to very high temperature, and there is a heat transfer from the hot gases to the blade material. There are many other situations, but these are the three typical situations which are very common. What will we study in this set of lectures on forced convection? This is a typical list of topics. First, we will restrict ourselves in this set of lectures to single phased forced convection. That means we are not considering situations where a liquid evaporates or boils into a vapor, nor a situation where a vapor will condense into a liquid, nor a situation where a liquid will freeze and form solid particles like water freezing into ice. Okay. These are two-phase situations, and we will keep away from them at least for the time being. After some initial discussion, we will look at some basic governing equations for forced convection. We will look at their rather simplified forms, because in the general case the governing equations of forced convection tend to be very complicated. Then we will look at three typical very common situations. One is flow through a tube, essentially a case of internal flow. Then boundary layer over a flat plate, a basic case of external flow, and flow across a cylinder, which also is a basic case of external flow. Whenever appropriate, we will be looking at the analogy principles, analogy between fluid flow and heat transfer, and we will make ourselves conversant with some correlations for these situations and maybe for some slightly different situations. Now we will look at the basic situation in forced convection. In forced convection, we invariably have a surface which is exposed to a fluid. Fluid may be liquid or gas. For the sake of illustration, let us assume that the surface is hot and the fluid is cold compared to each other. Okay. Let us take a point on the surface. Let us say that the temperature at that point on the wall of the solid is Tw. It would vary from location to location. If this is the position on the wall, it could be a function of x. Similarly, the fluid flowing across this at a reasonable distance away from the solid, so as not to directly feel the presence of the hot solid, let it be at a temperature Tf. The fluid may be getting heated up, so this temperature could also vary along x. Because the fluid is cooler than the solid, there will be a flow of heat from the solid to the fluid by convection. Let me say that the heat flux at that point is Q by A at the wall. And again, this may be varying from one point to another point. So let me say this is Q by A wall at that particular x. Our aim in forced convection is to determine a relation between the heat flux from the wall to the fluid and relate it to the temperature of the wall at that point and temperature of the fluid at that point. This is a local situation. We may not be interested in local variation of temperature, local variation of heat flux. So maybe in a gross way, in an overall way, let us say that I have a surface. Let us say the surface area is A. The mean temperature of the surface is Tw bar. There is a fluid flowing. The mean temperature of the fluid which is exposed to the surface is Tf bar. And let us say that the flow of heat from the solid to the fluid is Q over this area A. Here we would like to relate Q to the area A, the temperature Tw bar and the temperature Tf bar, whereas this is the average case, whereas here we would like to relate heat flux at the wall to temperature of the wall at that point and temperature of the fluid at that point. Naturally, this will not be related only to this, it will be related to the geometry, the flow rate of the fluid, the local velocity of the fluid and properties of the fluid. We have already seen in the introductory lectures that whenever there is a process of convection, a solid exposed to a fluid and heat transfer from the solid to the fluid by convection, we define a parameter known as the heat transfer coefficient. Considering the two situations which we looked at just now, the local situation and the average situation, we can define the local heat transfer coefficient and the average or the mean heat transfer coefficient. The local heat transfer coefficient may vary from one position to another, so we generally use a subscript x denoting the position for h. Hx is the local heat transfer coefficient, which is a ratio of the wall heat flux from the wall to the fluid at that location divided by the temperature of the wall at that location minus temperature of the fluid at that location. Notice that the heat transfer coefficient is always defined as a positive number. So if you have heat flux from the wall to the fluid, in the denominator you should have wall temperature minus the fluid temperature. If you use a heat flux from the fluid to the wall, which may be convenient if the fluid is warmer than the wall, then you will have heat flux from the wall to the fluid in the numerator, and in the denominator you will have the fluid temperature minus the wall temperature. On an average or mean basis, you can determine the average heat transfer coefficient or a mean heat transfer coefficient over an area A. So here we have defined the average heat transfer coefficient, denoted often as H bar or HAVE, as the heat flow rate from the wall to the fluid divided by the area. So Q wall to fluid divided by area gives us something like the average heat flux. Then that thing is divided by the mean temperature of the wall minus the mean temperature of the fluid. We should remember that the SI units for the heat transfer coefficients are watt per meter squared Kelvin. Heat transfer coefficients hardly ever go below a few watt per meter squared Kelvin. So we never have any reason for using milliwatt or microwatt. Large heat transfer coefficients do occur, a few thousand watt per meter squared or even a few 100,000 watt per meter squared are not uncommon in such situations. So if need be, we can use kilowatt per meter squared Kelvin. But somehow it turns out that watt per meter squared Kelvin is the most common unit. Now those of us, and almost all of us, are exposed to fluid mechanics, and we know that we tend to correlate all our data in terms of dimensionless numbers. So even the data for heat transfer in forced convection is finally correlated in terms of some dimensionless numbers. In a situation of forced convection, the significant parameters turn out to be the heat transfer coefficient, properties of the fluid, namely density, conductivity, viscosity. Here I have used dynamic viscosity, specific heat. Some geometric parameters, I have just included 1L as a reference length, and the flow parameter, the velocity of the fluid. If you use Buckingham's Pi-Theorem, we obtain the following three dimensionless numbers. One turns out to be H into L by K, another rho V L by mu, and the third Cp mu by K. This rho V L by mu, well, we already know that as Reynolds number, so there is nothing new about it. So the Reynolds number represents the flow properties of the fluid, flow situation of the fluids. The Nusselt number HL by K, similar to the Bio number, but remember, in the Bio number we have the conductivity of the solid, here we have the conductivity of the fluid. This Nusselt number is a dimensionless version of the heat transfer coefficient. So any heat transfer coefficient information or data is finally converted into dimensionless form in the form of the Nusselt number. The third dimensionless number, the second number specific to convective heat transfer, is the Prandtl number. And it is interesting to note that the Prandtl number Cp mu by K is a function only of the properties of the fluid, specific heat, dynamic viscosity, and thermal conductivity. We already know the significance of the Reynolds number from our fluid dynamics study. Let us look at the significance of the Nusselt number and the Prandtl number. we know that the Nusselt number is HL by K. Let us consider A to be the area across which heat transfer takes place, and we can rewrite this as L by Ka in the numerator and 1 over HA in the denominator. Now notice that the numerator represents the thermal resistance for a conduction situation. In particular, if we consider a slab of thickness L, area A and conductivity K, okay, a slab of fluid in which only conduction takes place of thickness L, this will be the thermal resistance for conduction. This, well, there is a heat transfer coefficient, so this is for the, in a similar situation, the thermal resistance for convection. So the Nusselt number represents the relative importance of the conduction thermal resistance and the convective thermal resistance. In a situation where forced convection effects are significant, we expect the convective heat transfer coefficient to be high, and hence the resistance to convection, RTH convection, which goes into the denominator, to be low, meaning we will have a high Nusselt number. So high Nusselt number represents very good convection situation. So if we have a situation of forced convection, a better situation, a more effective forced convection effects would mean that the Nusselt number is high. Prandtl number is special in the sense that it is a function only of three properties, and we can rewrite this as mu by rho divided by K by rho Cp. We know that mu by rho is the kinematic viscosity usually represented by nu, and K by rho Cp is the thermal diffusivity alpha. Notice that both have units of something like meter square per second, area per unit time. Okay. And what does the numerator represent? A high nu means a reasonably large viscosity. So this represents the efficacy of the fluid for momentum transfer. A viscous fluid will have a high value of nu. Alpha, on the other hand, notice that larger the conductivity means larger the alpha. Heat will be transferred faster by conduction. Lower the Cp means larger the alpha. Lower the Cp means for the same amount of heat gain, the temperature will rise significantly. So the alpha represents efficacy of the fluid for heat transfer. So Prandtl number in essence represents the ease at which a fluid is able to transfer momentum or shear forces to the ease by which the fluid can transfer heat. Naturally, we expect a fluid which has a high viscosity to have a high Prandtl number. A fluid which has a high conductivity will have a low Prandtl number. Since the Prandtl number is a property of the fluid and not of the flow situation, one should notice that for a large number of gases, Prandtl number is of the order of 1. Air at ambient temperature and pressure as roughly 0.7. You take oils, say lubricating oil, engine oil of a car. Here we have high viscosity. Prandtl number is of the order of or greater than 100. Prandtl numbers of 300, 500 are not uncommon, particularly for low temperature oil. If you take mercury, a liquid metal, low viscosity, high conductivity. Any other liquid metal as liquid sodium, liquid potassium, situations of high conductivity, comparatively low specific heats, comparatively low viscosities. Here the Prandtl number is of the order of or less than 0.01. So you will get a range of Prandtl numbers depending on the fluid and its state, pressure and temperature, going from something like 0.001 at one extreme with liquid metals and something like almost of the order of 1000 for viscous oils. After undertaking this basic discussion on forced convection, heat transfer coefficient, Nusselt number and Prandtl number, let us start looking at the governing equations for forced convection. The forced convection situation is characterized by a flow of fluid which already exists. There is also a heat transfer, so conductivity will play a part. Process of conduction will also be involved. So the governing equations pertaining to forced convection are the governing equations for fluid flow plus the governing equation for transfer of energy. So we will have definitely the continuity equation and the momentum equation. These two equations pertain to fluid flow. But now there is a heat transfer, heat is a form of energy, so the energy equation is required for heat transfer, for convection. And as we have already seen in the study of conduction, the energy equation by itself is not sufficient because it provides relations between heat fluxes. We have to relate heat fluxes to temperatures and temperature gradients by using the Fourier's law. So the equations for fluid flow will use continuity equation and momentum equations. The additional equations used are the energy equations, energy equation and the Fourier's law of heat conduction. Since we have studied the continuity equation and the momentum equations already, let us look at the energy equation. The energy equation represents the law of conservation of energy, the first law of thermodynamics. Now in forced convection we have a fluid system, something is coming into any control volume we consider, something is going out of the control volume. So we apply it in the open system form. So the general open system would be a control volume, some mass flow rate would be going out, some mass flow rate would be coming in, there will be heat transfer to the system, there will be shear work there could be shaft work, and even the energy of the system could be changing with time. Okay. The first law of thermodynamics relates all these quantities to each other. In the introductory part, the first few lectures, we have seen this reasonably general form of the first law of thermodynamics for a control volume. We have the heat transfer term, we have the shaft work term, we have the shear work term, we have the energy storage term. This is the net outflow of energy by convection, net inflow of energy by convection. And we have the kinetic energy term, the enthalpy term, and the potential energy term. In a typical, a general forced convection situation, many of these terms would be non-existent or negligible. We can get rid of them. For example, we will assume that steady state exists. So if you have steady state, this term will go away. We will assume that it's a pure heat transfer situation. There is no work being done. This term would be significant in case of turbines, compressors, pumps. It's not significant in case of boilers, condensers, heat exchangers, and so on. So this will be 0. We will also neglect shear work. In a large number of heat transfer situations, the shear work term doesn't exist. It's absolutely negligible. It becomes significant only in case of very high speed gas flows, high Mach number, almost hypersonic flows. So this also is negligible. Then we will also assume that the potential energy terms are negligible and the kinetic energy terms are also negligible. So you will notice that the general form of the energy equation will end up with some very gross major simplification. And this simplification leads to this simplified form, which is directly pertinent to forced convection heat transfer. And you will notice that we have the heat transfer to the control volume, and on the right hand side we have the total net outflow of enthalpy. This is the outflow of enthalpy from parts of the control surface where the fluid goes out. We have denoted it with this subscript O, and this is the inflow of enthalpy over the part of the control surface where the fluid is coming in, as denoted by the subscript I. And notice the assumptions: negligible shaft work, negligible shear work, negligible changes in kinetic and potential energy, and also steady state. Now our aim is to finally derive a differential equation for forced convection, just the way we derived earlier a differential equation for conduction. We do that by applying this equation to a small control volume. First, we will apply it to a control volume and model the Q term. Next, we will model the enthalpy outflow and inflow terms. To obtain an expression for Q, let us consider Cartesian coordinates, and let us also consider a two-dimensional situation. Let us say we have, this is the x direction and this is the y direction. And let us say in our fluid domain, let me draw a control volume. I am drawing it large so that I can mark out the heat flow rates. Let us say the extent is from x to x plus delta x and from y to y plus delta y. Just for convenience, you could even take x minus delta x by 2 to x plus delta x by 2. We will have heat flowing in by the process of conduction from here and here, and heat flowing out like this. I am showing heat flow rates in the positive x and positive y direction. Now let us use Fourier's law of conduction to write expression for these 4 heat flow rates by conduction. This heat flow rate would be minus k dt by dx, that is gradient in the x direction. We are looking at the heat flow by conduction in the x direction, multiplied by area, which will be delta y into 1. Let us say we are considering a control volume which is unit thick perpendicular to the plane of the paper. So this is delta y. A similar term will occur here, minus k dt by dx into delta y. The difference is this term is evaluated at x location on the x coordinate. This term is evaluated not at x but at x plus delta x. Okay. Similarly, this heat flow from the lower edge will be minus k. We are looking at heat flow in the y direction, so dt by dy partial multiplied by area, which will be delta x into 1. Similarly, on the other side we will have a very similar term, minus k dt by dy into delta x into 1. Again, this term is evaluated at the bottom end of the control volume, which is at y, and this term is evaluated at the opposite end of the control volume, which is y plus delta y. Okay. Notice that when we evaluate this term and this term, y doesn't change. So let's look at x and x plus delta x. Similarly, when we evaluate these two terms, they are at some fixed value of x. Y only changes. We now write these down together as the Q term in our first law of thermodynamics. Notice that the 4 terms shown in the previous figure are all represented here, but since Q is inflow, these 2 terms will contribute positively. These 2 terms would effectively be subtracted because the arrows move out of the control volume. So we have the 2 inflow terms and the 2 outflow terms with a negative sign. Now we go back. We have now modeled our Q term. It is now necessary for us to model the enthalpy outflow terms. Again, to model the enthalpy outflow terms, we have the same coordinate system, x and y, and let me re-sketch that control volume whose extent was from x to x plus delta x and y to y plus delta y. Now mass flows in and out, and along with the mass, enthalpy will be convected. So there is a mass flow like this, some mass flows out like this, there is a mass inflow like this, there is a mass outflow like this. Let us look at this term. The mass flow here would be rho into Vx into area, which will be delta y into 1, and the enthalpy which is being carried by that is h. So the enthalpy inflow through this phase is rho Vx delta y into h. Similarly, there will be an enthalpy outflow here, rho Vx delta y into h. The difference, this is at location x at the left edge of the control volume. This is at location x plus delta x, which is the right edge of the control volume. Let's look at these two enthalpy flows. The mass flow in here will be rho into Vy. We are now looking at the flow in the y direction. Area will be delta x into 1. It carries with it enthalpy h. And a similar term here, rho Vy delta x h. But the difference, this term is evaluated at y, the lower edge of the control volume. This term is evaluated at y plus delta y, which is the upper edge of the control volume. We combine these four terms. Remember, what we want is enthalpy outflow. We have two outflows here and two inflows. So we will have two terms contributing additively and two terms contributing in a negative way. So this is what we get. The enthalpy outflow terms, these are the sum of the outflowing streams. This is the sum over incoming streams. We have two outflowing streams and two incoming streams. So these four terms together represent these two terms. Now we have an expression for the Q term, we have an expression for the other two terms in the first law of thermodynamics. We will now combine these terms, and the resulting equation we will try to convert into a differential equation by taking the limit as delta x tends to 0 and delta y tends to 0. When you do that, this is what you will end up with. On the left hand side of this equation, we have terms containing conductivity and temperature gradients, both in the x direction and y direction. This is the final form of the Q term of our first law of thermodynamics. On the right hand side, we have terms containing Vx, Vy and H. These are the enthalpy outflow terms, the final form in the differential equation of the enthalpy outflow terms. You should immediately notice that if Vx and Vy are both 0, there is no fluid flow taking place, then what we have obtained is nothing but the conduction equation. The right hand side becomes 0. Now, although this is a proper energy equation, it is not directly useful because we have temperature and we have enthalpy. So we relate enthalpy to temperature by noticing that the derivative of enthalpy with temperature is defined as the property Cp, specific heat at constant pressure. What we also do is we expand these terms, and once we expand these terms and assume constant properties and incompressible flow, we will find out that a number of these terms get cancelled out because they satisfy the continuity equation. So what we do is expand these terms, use the continuity equation for simplification, and replace H in terms of Cp and T. When we do that, this is what you will get. I have written it in a form which you will generally find in textbooks. So you have the enthalpy outflow terms on the left hand side and the net heat inflow terms on the right hand side. So these terms are the terms representing enthalpy outflow, and these are the terms representing Q, the net heat inflow. Quite often these are known as the convection terms, and these are known as the conduction terms. Sometimes also called diffusion terms. Okay. Again, you will notice that if Vx is 0 everywhere, Vy is 0 everywhere, then this equation, energy equation, reduces to the conduction equation. A very common situation in forced convection heat transfer is flow through a duct, particularly circular ducts. I think flow through a circular duct is one of the most common, overwhelmingly common forced convection heat transfer coefficient. And the Cartesian coordinate system is not a useful system for flow through a circular duct. To analyze flow through a circular duct, which we will do slightly later, we convert the energy equation from Cartesian coordinates to cylindrical polar coordinates. So again, remember that this is a simplified version which is valid for the steady state, constant property situation, incompressible flow situation, and axisymmetric situation. It also assumes that temperature Vr and Vz, these are functions of only the radius and the axial coordinate z, and there is no swirl, and that means V theta is 0 everywhere. In case of a swirl situation, you will have to consider non-zero V theta, and appropriate terms will enter not only in the momentum equation and continuity equation, but even in the energy equation. Again, in this energy equation, notice that on the left hand side here we have the convection terms, and here we have the conduction terms. After this basic derivation of the governing equation, the most important governing equation being the energy equation for situations of forced convection, we now move to analyze and look at three typical situations. The first one is heat transfer to a fluid flowing in a tube. We will consider steady laminar flow, and we will consider two situations represented by two basic boundary conditions. These are the thermal boundary conditions on the wall. One is if the wall is maintained at a constant temperature, and the other when the wall is exposed to a constant heat flux. This happens, and it's a good approximation if the wall is directly heated by resistive heating or the wall has a heating coil wound over it. We will study each of these in turn, but let me sketch and show you what we mean by the two situations. The first one, a constant wall temperature situation. The temperature here will be T wall is constant. This is the inner surface of the tube through which the fluid is flowing. And let the inlet temperature of the fluid be TFI. And let us assume for the time being that TFI is less than T wall. Let us consider this case. Let us say T wall is something like 90 degrees C and TFI is something like 30 degrees C. What will happen? The wall is warmer than the fluid, so there will be a heat flow from the wall to the fluid. And this TF will go on rising as the flow proceeds. From 30 degrees C it will go to 40 degrees C to maybe 60 degrees C. But in any case the TFE exit temperature will always be less than 90 degrees C, because the fluid will never be able to heat up beyond the wall temperature. This is the situation of constant T wall. The other situation is that of a uniform heat flux on the wall. Q by A at the wall is maintained at some constant value, say 1000 watt per meter square. So we don't talk about the wall temperature, it's not specified. Let us say the fluid enters at a temperature TFI. Let us say 30 degrees C. What happens is it gains heat from the wall at a uniform rate. Since we have a steady flow, this will go on rising almost uniformly. So you will end up with 40 degrees C, 50 degrees C, 60 degrees C. It will go on rising. What is the exit temperature? There is no limit. It will have to be calculated based on the area, the amount of heat flow. The wall temperature will also need to be calculated. It will vary along Z. We will have to determine what it is. Exit temperature will also have to be determined. Here, temperature will also have to be determined along the fluid flow and the exit temperature, but the wall temperature is maintained. This is the constant wall heat flux situation. In this lecture we stop here. In the next lecture we will consider in detail first the problem of heating with a constant wall heat flux, then the problem of heating with a constant wall temperature. Thank you.